Welcome back. Today we're diving into, well, pretty much the most fundamental map of reality physicists have, the standard model of particle physics. It's often called the toolbox of the universe. It tells us what everything's made of, doesn't it? And how it all sticks together.
It certainly does that for the stuff we know and can see. It lists all the known elementary particles. And maybe more impressively, it describes 3 of the 4 fundamental forces with, frankly, mind-boggling accuracy. It's a huge achievement of 20th century physics.
But you're saying there's a catch?
Oh, a big one. We know for sure it's not the final word. You could almost call it the most successful failure in science, because while it works incredibly well for what it covers, it misses some enormous things.
Okay, let's start with what it does cover. The building blocks, the fundamental bits of matter.
Fermions, right?
That's them. The bricks, you could say.
Yeah.
And they fall into 2 main families. Quarks, which build protons and neutrons inside the nucleus.
And leptons, like the familiar electron orbiting the nucleus. Exactly. But here's where it gets, well, a bit strange. Both quarks and leptons come in 3 distinct generations.
3 generations. I thought, up and down quarks plus the electron and its neutrino, that makes up pretty much all ordinary matter.
It does. That's the first lightest generation. Everything you see, touch, interact with is all first generation stuff.
So why the other 2, heavier copies?
Yes, essentially heavier, unstable copies. The second generation has charm and strange quarks, the muon and its neutrino. The third has top and bottom quarks, the tau and its neutrino. They decay almost instantly.
And we don't really know why nature bothered with the extra copies.
That's one of the big unanswered questions baked into the model itself. Why 3? Why this structure? We don't have a definitive answer.
Huh. Okay, sticking with quarks for a second, they have that unique property, color charge. Not actual colors, though.
Right, not visual color. It's a type of charge, like electric charge, but for the strong force. There are 3 types, red, green, and blue, plus their anticolors. And the crucial rule is that quarks can only exist in combinations that are color neutral or white. So you need like a red, green, and blue quark together in a proton.
Or a quark and an antiquark of corresponding color-anticolor.
Precisely. If that rule didn't hold, quarks couldn't bind together stably. No protons, no neutrons, no atomic nuclei. It's absolutely fundamental.
Okay, so we have the fermion blocks. What about the forces holding them together or letting them interact? That's where bosons come in, the messengers.
Exactly. Gauge bosons. They carry the forces. The most famous one is the photon, the particle of light carrying the electromagnetic force.
Simple enough. What about the strong force, the one gluing quarks?
That's mediated by gluons. There are actually 8 different types of them. It's a very strong force, hence the name, and the theory describing it is called quantum chromodynamics, or QCD. Think of it as the rule book for quark interactions.
And the third force in the model, the weak force.
Yes, the weak force. It's responsible for certain types of radioactive decay, like beta decay. It's carried by 3 heavy particles, the W plus can, the W, and the Z boson.
Finding those must have been a huge deal. I remember reading about CERN in the 80s.
Absolutely massive. When Carlo Rubbia and Simon Vandermeer led the experiments that found the W and Z bosons at CERN, matching predictions precisely, that was spectacular confirmation. Nobel Prize, rightly so.
Yeah.
It really cemented the electroweak part of the theory.
Okay, blocks and messengers, but what about mass? Where does that come from? That brings us to the Higgs boson, doesn't it? The big player discovered relatively recently.
The final piece found, yes, in 2012. The Higgs boson isn't so much the giver of mass, but rather the evidence of the Higgs field.
A field that permeates all of space.
Exactly. Think of it like cosmic molasses everywhere. Particles acquire mass based on how much they interact with or sort of struggle against this field.
So particles like the W and Z bosons, the quarks, the leptons, they interact a lot, get bogged down, and gain mass.
That's the picture. The more they interact, the more inertia, the more mass they have.
And particles like the photon, the carrier of light, and the gluons.
They barely interact with the Higgs field at all, or maybe not at all. That's why they're massless, or very nearly massless. They zip right through the molasses without resistance.
So the picture seems complete. Fermions are the matter, bosons carry the forces, the Higgs field provides the mechanism for mass. It sounds incredibly elegant.
It is incredibly elegant. That's right.
But you started by saying it's incomplete. Where are the cracks? What's missing?
Well, the biggest, most glaring omission is gravity. The standard model says absolutely nothing about it. We have Einstein's general relativity for gravity on the large scale, and the standard model for the small scale, and they don't fit together at all.
That's a pretty fundamental gap. Trying to unify those is a major goal of physics.
The major goal. arguably. But
Mhm.
there's another huge problem, maybe even more humbling. All the particles and forces described by the Standard Model, everything we just talked about, that only makes up about 5% of the total mass and energy in the universe.
Only 5%. Seriously.
Seriously, about 25% of the universe seems to be made of dark matter, some kind of invisible matter we can only detect through its gravity. The Standard Model has no particle candidate for it,
Okay.
and the remaining 70%. That's dark energy, some mysterious force causing the expansion of the universe to accelerate. Again, the Standard Model is completely silent on this.
So our best map of reality describes just a tiny fraction of reality itself.
Precisely. We've mapped a small island chain in incredible detail, but we have almost no idea about the vast oceans surrounding it.
And there are still those nagging internal questions like the three generations or the fact that neutrinos do seem to have a tiny bit of mass, which the original model didn't predict.
Exactly. Those are clues, hints that there must be physics beyond the Standard Model. Neutrino mass in particular is strong evidence.
So we have this incredibly predictive, verified model that describes only 5% of everything. Where does that leave us?
It leaves us with a profound mystery and a huge task. It tells us the universe is far stranger and more complex than even our best theories suggest. The big question for you, for all of us, is what the heck is the other 95%? What new particles, new forces, maybe even new dimensions are waiting out there? The search is definitely on.